This video clip is part of the EPFL introductory course on information, computing, and communication. It is the 7th one in a set of video clips on memory hierarchies and management. It explains what happens in a hypothetical hierarchical two-level memory built out of a cache and a main memory when the processor wants to access a word that is not in the cache and the cache has no room left to import it into main memory. In this case, room needs to be made in the cache, which implies that some other block must be ejected from the cache. Which other block is selected for ejection is the key to efficient performance of memory hierarchies. And that key lies in an algorithm that always selects the least recently used block for ejection. That algorithm is abbreviated LRU. In the present example, the processor is assumed to want to read the word at address 4, but the block containing word 4 is not in the cache, and there is no room left for it in the cache, which is already full. The LRU algorithm will make the required room by ejecting the block that has been the least recently used, under the assumption that that block is no longer needed. The challenge is how the cache can know which one is the least recently used among all the blocks in the cache. To address this challenge, the cache needs to be equipped with some new extra hardware. Concretely, for every block in the cache, there is an additional register that contains as many bits as there are blocks in the cache. Every time the processor accesses the cache, the register of the block that is now being addressed is set to 1, and all other block registers are shifted by 1 to the left. Thus, every register always contains a number equal to a power of 2. The block whose register is the largest, power of 2, automatically designates the oldest unused or least recently used block. This is the one that the cache will then select for ejection to make room for the newly needed block to be imported. So back to our step-by-step simulation, the processor issues the cache a command to read word number 4. The cache computes that the requested word is in the 4-word block starting at address 4, which is not yet in the cache. The processor is thus forced to wait before reading the word until it can be imported from main memory into the cache. But the cache is full. The cache thus follows the hardware LRU algorithm to select the least recently used block, the one with age 2 in this example, and erases it to make room for the new block. As in the case when the cache is not full, it then proceeds to send the main memory a command to transfer the missing block from main memory into the cache. The main memory then sends back to the cache the entire 4-word block, including word number 4. And as usual, the cache safely saves this block into the now freed block, and it updates the block usage registers as per the least recently used rule. The last challenge to be addressed is what happens when the LRU block to be ejected has already been written into by the processor. In that case, it cannot just be erased because then its updated values would be lost and return to the old values still in the main memory. In this case, the first step is still the same as usual. The processor issues a command to the cache. To address this last challenge, the cache needs yet another bit of hardware, a 1-bit register for each cache block. This bit is set to 1 if and whenever any of the 4 words in the corresponding block is written into by the processor. If and when the cache determines that a least recently used block must be ejected, it first checks that extra write bit. If the bit is set to 1, the cache knows that it must first write the block back to main memory before importing a new block. Then the cache resets the right bit of that block to 0 and proceeds as usual, erasing the LRU block to make room for the new one. The main memory then provides the newly required block, and the cache saves it in its free block, updates the usage registers, and all is back to normal.